This video will show you how to use the calculator to solve a system of equations with three variables. Specifically, you will input a matrix and the calculator will process the matrix into row-reduced echelon form. In this form, all of the unknown variables are solved for you. There is no need to do any back substitution as you did when the matrix was in reduced echelon form, as seen in the video Matrix Reduced Echelon. However, there is one exception. When there are infinitely many solutions, you will need to do back substitution to get a general solution. Example number 1 will have one solution. Use a matrix in row-reduced echelon form to solve the following system of equations. Negative x plus y plus 2z equals 0. X minus 2y plus 2z equals 2. And 3x plus 2y minus 2z equals negative 1. Let's input the system of equations into the calculator. So remember, we need to go to second function in matrix, and then we already have matrix A set up as a 3 by 4. So remember, that means 3 rows by 4 columns. And we want to edit that, so we will move over to Edit and select Enter. Okay, let's input the following values. Negative 1, enter, 1, enter, 2, enter, and 0. 1, enter, negative 2, enter, 2, enter, and then 2. 3, enter, 2, enter, negative 2, enter, and finally negative 1. Okay, so as was mentioned before, we need to completely quit out of the matrix mode and get back to the main screen in order to do the matrix operation. So go second function and quit. So now we're here at the main screen. Let's get back into the matrix mode, second function matrix, and we want to go to math, and we want to find the RREF. So this is what we used before, REF. Now we want RREF, which is row reduced echelon form. Select Enter, and we want that for matrix A, so go second function matrix, and then A, select Enter, and close the parenthesis, and now select Enter again. Now we have our row reduced echelon form matrix, and if you notice, in the first row, what's unique about the row reduced echelon form is that we have 1 for 1x, and then the rest of the entries are 0 for all the variables. And then finally, it gives you a solution, 0.25. Okay, let's look at row number 2. Okay, we have 0x, we have 1y, and we have 0z, and then that will equal to negative 0.5. So that means y is equal to negative 0.5, and finally we have the third row, where x is 0, y is 0, and we have 1z right here, and that's equal to 0.375. Okay, so x will be equal to 0.25, y will be equal to negative 0.5, and z will equal to 0.375. Now, these are written in decimal form. Okay, now recall that we can express these decimals in fractional form. So if we want to do that, let's go back to our previous keystroke, and you do that by going second function, and that operates the entry key right here. So we'll select this key, and then now we're going to go to the math mode and use frac. Select enter and then enter again. Okay, so let's go ahead and look at the conversions, and here we have them. So the 0.25 is now 1/4, the negative 0.5 is negative 1/2, and the 0.375 is 3/8. Okay, I would highly recommend entering your answers in fractional form. So the final solution then is going to be x is equal to 1/4, y is equal to negative 1/2, and z is equal to 3/8. Alright, let's clear the screen. Now, for example 2, this system of equations will have no solution. We would like to use a matrix in row-reduced echelon form to solve the following system of equations. P plus 3Q plus 2R is equal to 0. 4P plus 17Q plus 23R is equal to 5. 3P plus 11Q plus 12R is equal to 9. Okay, we will go input these equations into the matrix. So go second function, matrix, and we're going to matrix A. It's already set up, 3 by 4. So we'll move over to edit. We'll select enter. Okay, now let's change these values in each cell. Okay, so we want 1, 3, 2, and then 0. It's already there, so I'll just select enter. Then we want 4, 17, 23, and 5. Then we want 3, it's already there, so select enter. Then 11, and 12, and then 9. Okay, again, let's get out of the matrix mode completely. So second function, quit. Now let's go back, second function, matrix, go to math, and we want RREF. There it is. Select enter, and we want that for matrix A. So second function, matrix, select enter, close the grouping symbol, and then enter. So the system of equations to the right come from the row-reduced echelon form matrix. That is, P minus 7R is equal to 0, Q plus 3R equals 0, and 0 is equal to 1. So let's go ahead and take a look at the first row, and we have the P, and then there's no Q, and then minus the 7R, and that should equal to 0. There it is. And the second row represents the 0P plus 1Q plus the 3R, and that's equal to 0. And then the third row, we have all zeros on the left hand side. So we have 0P, 0Q, and 0R. So we have 0 on the left, and that's equal to 1 on the right hand side. Now recall that 0 equals to 1 is not true. It's a false statement, and therefore the system of equations is inconsistent, and that means that there is no solution for this particular system of equations. For example 3, we will have infinitely many solutions for the system of equations. So use a matrix in row-reduced echelon form to solve the following system of equations. X plus y plus z equals 4. X plus 3y plus 3z equals 10. 4x plus 8y plus 8z equals 28. Okay, let's input these into the calculator. So second function matrix. Again, matrix A. Move over to Edit. Select Enter. Let's put in the correct cell values. So let's move down. Okay, 1 is fine. We'll move over. 1, and then Enter. 1, Enter. And then 4, Enter. 1, Enter. 3, Enter. 3, Enter. 10, Enter. Then 4, 8, 8 again, and 28. Okay, again, let's quit out of the matrix mode. So second function quit. Let's go back into the matrix mode, and then move over to math. Now let me show you a quick little tip here. I've been moving the arrow down to find the RREF. So let's move it up, and you notice it comes up right away. So you can use the arrow up or down depending on where your specific option is. It may be easier to use the up arrow instead of the down arrow. So let's move to RREF, select Enter, and we want that for matrix A. So second function matrix, and then Enter. Close the grouping symbol, and select Enter. Okay, so here's the matrix in reduced row echelon form, and to the right of the screen you have the system of equations that relates to this matrix. So we have here that x, or 1x, there's no y, and no z, equals 1. So x equals 1. And let's look at the second row. Right, and that says that there is no x, there's 1y plus 1z equals 3. And then finally the third row, you can see that the left-hand side has all zeros, so 0x, 0y, and 0z is equal to 0. Now we have a true statement here for the third equation, and that says 0 is equal to 0. That is indeed a true statement, and this tells us that there are going to be infinitely many solutions. So what we need to do is remember we need to take the third variable, or the last variable in the system of equations, which happens to be z, and we'll set that equal to some parameter. And this parameter will be t. So we're going to let z equal t. Now this is where we need to use back substitution. Since x is already solved for, it's equal to 1, then we only need to solve for y. So we will use back substitution to solve for y, and you end up with the following general solution. We have x is equal to 1, y is equal to 3 minus t, and z is equal to t. So this is called the general solution. Now we're going to substitute any value that we would like into t, and this is where the infinitely many solutions comes into play. So for whatever value of t we choose, we'll get a solution back for x, y, and z. And there are infinite choices that we can choose for t. So let's pick a couple easy values. If t is equal to 0, then x equals 1, y equals 3, and z equals 0. If t is equal to negative 3, then x equals 1, y equals 6, and z equals -3. So what's unique about this system of equations is that x will always be 1, and the only two variables that change are y and z, and they are dependent upon the value that you choose for t. Recall, as I mentioned before earlier in this video, that for a system of equations that have infinitely many solutions, you will have to do some back substitution. Now remember, in example 1 you did not need any back substitution because each variable was solved for you individually with the row-reduced echelon form. And for example number 2, there was no solution, so there was no need at all to do any back substitution. Okay? This concludes the video on using the matrix row-reduced echelon form.